Hello, welcome to Einstein's Mechanics. In this episode, we are going to start with basic or applied electronics. So, we are going to dive deep into the various subtopics in episodes so that you have to get time and understand everything. Are we okay? So, in today's episode or the episode that you'll be watching, we are going to tackle the semiconductor physics. We will also look at diodes and its applications. We will also talk about transistors and thyristors. So this and many more are the study areas for the basic or applied electronics. But before that, let's get some definitions. We have to understand certain terms that will help us through our studies. So, basic or applied electronics or electronics in general. Before we dive deep, let's understand the basic definitions. So, the first part that we are going to look, we will have what we call a conductor. And when we say a conductor, we are talking about a material that is having a high electrical conductivity. So, any material with high electrical conductivity is called a conductor. This means electrons can flow through such a material to produce what? A current. So when you look at the diagrams down here, you see that the first part, this is a conductor and it is a copper wire. So this copper has the ability for electrons to flow through, and as they flow there will be current generated. All this we will look at them and how they occur. So we now have an idea of conductor, any material having high electrical conductivity. Pay attention to the word high so that we will get the difference between various materials. So conductors are high, and when we talk about an insulator, is also a material having low. So they are all talking about electrical conductivity, but what qualifies them here is the high, is the low, and is the medium. So for insulators, they have low electrical conductivity. We do not want to say they do not conduct at all, because in some instances they may, but it is very low. Are we okay? And sometimes too, before the electrons will flow through the insulator, let's say they have high gap or the band gap. We will explain that the band gap in insulators is very high, so it will be impossible for electrons to cross to the conducting band. And before they even do that, if you apply more heat, the insulator will begin to melt, and that makes them low in electrical conductivity. Are we okay? So when we look at the second diagram, we mostly see this on cables. Yes, when we look at the high tension and most of the electrical cables, we will see such discs, and they are all insulators. Are we okay? So this is a disc-shaped insulator where we use in electrical connections. Are we okay? Now, since we have a conductor and insulator, there should be something in between them, and we call that as what? Semiconductor. And in basic terms, we will say a semiconductor is a material whose conductivity lies between conductor and what? Insulator. That is also right. It is semi of what? A conductor. But then also we will have to derive another explanation which says it is a material having electrical conductivity which is strong function of temperature, purity, and optical excitation. Because of this electronics course, we will have to stick to this explanation, because everything is going to be centered on semiconductor, and we are also going to look at how this temperature is going to affect it, how the purity is going to affect it, and how the optical excitation is also going to affect the semiconductor. So, in as much as we know it is a material which conductivity lies between conductor and insulator, we will also have to understand that its electrical conductivity is a function of temperature, purity, and optical excitation. So it says, for example, near absolute zero, high purity silicon is an insulator. Are we okay? So can we see that temperature here, absolute zero, which is when we look at the absolute scale, zero, at that temperature, silicon, which is acting as a semiconductor, will now turn to an insulator, meaning the temperature plays a role in semiconductors. And the purity, we will talk about doping and stuff, so that we also look at how the purity affects the conductor. Are we okay? So when you look at the third image here, we have some semiconductors. So we can see diodes, or this is a resistor. We can also see capacitor and diodes. We also have transistors and op amps. All these are semiconductors, and they are very important in the electrical circuits. Are we okay? So let's also look at this. We have various materials and their structure. As far as we are going to look at materials and how to apply them, it is very important we know the structure of the materials. So we have three of them, and first we are calling it as the crystalline solid. So when we talk about crystalline solid, we mean materials having a three-dimensional periodic array of atoms, or in simple terms, crystalline solids, we can have a 3D view of their internal structure. Are we okay? So when you look at such image, they are all crystalline view. When you want to look at their arrangement under a microscope, you can see that it is well arranged. Or crystalline solids are solids which has well arranged what? Structures, internal structures. Very simple. Are we okay? And when we talk about polycrystalline solids, it has several of the crystalline solids or shape that makes it poly. So many crystalline structure that makes it what? A polycrystalline solid. So this type or this kind of solid has several of the crystalline solids, so they are predicted. Their shape can be well seen. 3D view can be seen. Are we okay? And when we talk about amorphous solids, they are materials with no periodic structure. So when you check their structure, you cannot, it is not well defined. Look at this image. It is not well what? Defined. They have irregular shapes. So this structure that we are talking about is not the physical view of the material, but rather the internal view of the material. So those materials, when you view them under high microscope, or when you use a high electrical or electromagnetic microscope, you are going to see that their structure is not predicted. It is in a haphazard structure. Are we okay? So these are the three classification of structures that we are going to look at in terms of materials. And also we also have to get used to these terms. We are going to talk about electron, and when we talk about electron, we are talking about a negatively charged particle. So in our studies, anytime that we mention electron, we are talking about the negative charges. Are you okay? And these charges are what causes current to flow. So we are interested in how these electronic devices are going to help us to control our current, our voltage, And we cannot do that without electrons. The presence of the electrons are going to help us to generate such currents. So negatively charged particles are what we call electrons. Now we will also use the word as hole. And anytime we talk about a hole, we are talking about the absence of an electron in a crystal bond. So anytime there's an absence of an electron, it tends to be what? It creates a hole. And that hole is a positively charged particle. Are we okay? So for example, when we look at an atom which is negatively charged, if we lose this electron, the atom is now going to be positive charge. So the absence of an electron creates a positive charge, and that positive charge is what we are referring to as what? A hole. It's very simple. Are you okay? All right. So in discussing semiconductors, we are also going to come across the word intrinsic semiconductors and extrinsic semiconductors. Now, we saw that from the previous slide, it was stated that the property of semiconductors depends on some parameters, such as what? We have temperature, right? We also have, it depends on purity. So here, the purity is going to differentiate between intrinsic and extrinsic semiconductors. So a semiconductor, we want it to conduct electricity or to be able to have current flow in a certain way that we want. So in that case, we have to introduce some materials into the semiconductor. We will look at all this, how it is done. But a semiconductor which has no impurity atom, or it has an insignificant amount of impurity, it is called intrinsic semiconductor. So if we have a semiconductor which is pure from its natural state, let's say if it is positive, positive, positive by its natural state, we are not adding any impurity atom. We are not bringing in any negative into the semiconductor, such that whatever operation the semiconductor is operating is from its raw or natural state. That semiconductor is what? Intrinsic. Nothing has been done to it. The conducting ability is what? Due to how it is made or how it exists already. But then if we add impurity to control the electrical property, then that semiconductor becomes what? Extrinsic. So let's say we have this semiconductor, and at its natural state, it is able to help us generate, let's say, 5 amps current, or it's able to conduct 5 amps. But then it is too much for us. We want to reduce the conducting ability of that semiconductor. So here we are going to introduce an impurity. When we talk about impurity, anything that is not part of the original state becomes an impurity. So we are going to add an impurity, say a negative, to this original semiconductor. So now its conducting ability is going to fall to say 3.5 amps. So in that case, we have used impurities to control the electrical property of the semiconductor, and that becomes an extrinsic semiconductor. I hope it is well explained. And we have dopants. So I was talking about impurities being added to semiconductor to alter its electrical conductivity. So when you add that impurity is termed as a dopant. Are you okay? And the activity of you adding is called doping. So doping and dopant. So here, a specific impurity atom which are incorporated in controlled amounts. So we have controlled amount for the express purpose of increasing the concentration of electrons or holes. So basically the idea, when you look at the diagram here, the idea is that we are either adding a negative to the structure, the atom, in order to increase the electrons, or we are going to add positive to it. This positive adding means we are going to take out the electrons so that we will be left with what holes, that the positive charges, in a way to alter the conductivity of this silicon atom. Very good. So anything we add to increase electrons or holes becomes a dopant, and the activity of doing that is what called doping, adding impurities to. So doping means adding impurities to an atom or to an element. Are we okay? That's doping. And inside this structure, you can see that, as I said, we are either trying to add a positive or a negative to that. And in a case where the impurity atom increases the concentration of mobile atoms, we are calling it as well donors. So when we are adding more electrons, that's the negative charge or particles, they are what we call the donors. They are going to increase the concentration of what? Mobile electrons. Remember, in the conductivity of electricity, we saw that it is the electrons that are going to move to cause the current flow. So when we want to increase the electrons concentration, then we are saying the electrons becomes the donors in the structure. And if we also want to increase the concentration of what? Holes, they become what? The acceptors. Very good. So the acceptors are referring to the positive charge, and the donors are referring to the negative charges. It is very simple. So once we have all this idea, it is quite easy for us to understand basic explanations. So we also talk about major carriers and minority of the carriers. Now, if we take a semiconductor where we have, let's divide it into two. We have the positive section. Let's say there are some negative, positive, positive, negative, positive. Here we have negative and some combination of some positives. We have two sections of this, but we are taking this part A and this part B. So at part A, the most abundant charges in the semiconductor are what we call the majority carriers. So at part A, the majority carriers are what? The electrons, right? Electrons are the majority of the charges. And at part A, the minority, those less abundant, they are also what? The holes or the positive charges. And at the B section, the majority carriers are what? The holes, positive charges, and the minority are the electrons. So we are going to use these words, the majority and the minority. Those abundant are the majority, those less abundant are the minority. All right, so we are also going to pick various semiconductors, and you'll be hearing the word N-type and P-type materials. Here, N-type is a semiconductor having electrons as the majority carriers, and the P-type is having holes as the majority carrier. It is very simple to differentiate. N means negative type, P means positive type. So you don't need to worry yourself. Anytime the negative, which is the electrons, are many, it becomes what? N. So the part A, from what I do, the majority are the electrons, so meaning the negatives are many. So this is an N-type, negative type semiconductor or material. And at part B, the holes, which are the positive charges, are many. So it becomes what? A P-type, positive type. So this should help you to understand and differentiate between N-type materials and P-type materials. Don't worry about the electrical conductivity here. It was just showing you that we are going to have this part is P, this part is N. So when you look at this part, it has more of the positive charges as compared to the negative charges. We will explain why the negative charges are coming towards the positive side and why positive side are also coming towards the negative side. It is very interesting. Now we also look at various semiconductors. So we are going to talk about, you have a diode. When we say a diode, what do we mean? We are going to have a diode. A diode is a two-terminal device with p-type and n-type regions in which the electrical behavior differs for forward and reverse bias. So we are going to look at a diode as having two terminals. So look at the diagram here. So two terminal, this is terminal 1 and terminal 2. And here in a diode, one of the terminals is going to be p-type. Remember, we just said the p-type has more of what? The holes, the positive charges. And the other part will be the n-type, which means it has more of what? The electrons, the negative charges. So anytime you see this diode, this is what comes in mind. It has one side to be a positive type material, so positive, 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 and the other side being negative, negative, negative. It is rich in what? Electrons, and the other side is rich in what? Holes. And we are also going to discuss the forward and the reverse bias, and it is very interesting. We'll explain that. Now, another semiconductor we are going to consider is a transistor. Here, the transistor is having a three-terminal. It is a three-terminal device which the voltage or current at one terminal controls the electrical behavior of the other terminals. It is very interesting. Now let's look at, this is the symbol for a diode. So anytime you see this symbol, it is what? A diode. It's an arrow like this. With this becomes what? A diode. So transistor, it has three terminals. Diode is having two and transistor is having three. And with the behavior of transistors, this is a transistor, so this is what we are looking at. With its behavior, when you control voltage at one of the terminals, it is going to alter the behavior of the other terminals. Or when you control the current, let's say if I control current on terminal 3, it is going to alter the behavior, the entire electrical behavior of the other terminals. Are you okay? So meaning if we are connecting the three terminals for our connection, we don't need to worry ourselves in changing everything or what is happening at the three. We just have to change the input on one of the terminals, and it is going to affect the behavior of the other two terminals. That is a transistor. We will dive deep and explain with equations how to solve various problems. So the three terminals, we have what we call the terminal 1, we call it the emitter, the 2 we call it the base, and the collector as the third terminal. We'll have an episode to explain fully the transistor. Now we will end here with the field effect transistor and bipolar junction transistor. Remember, we are saying transistor is what? Three terminals where we control voltage on just one of the terminals or current on just one of the terminals to control the behavior on the others. So in a situation in which we control voltage at only one terminal to control the electrical behavior of the other terminal, that type of transistor is called a field effect transistor. Remember, when the field effect should even give you a clue. You know, the voltage is generated by the field. When you study the magnetism, you understand it very easy. So that's what we mostly call it the FET, that is field effect transistor, meaning we are using voltage on one terminal. Let's say if we control voltage at the emitter, it is going to alter the behavior of the base and the collector. Or if we try to alter current on one of the terminals to control the electrical behavior on the others, it becomes a bipolar junction transistor, BJT. Are we okay? So although they are all transistors, but if I mention a bipolar transistor, you should know that current is being controlled on one of the terminals. And if I say field effect, voltage is being controlled on one of the terminals. So this is just the introduction, the basic understanding you need in order to dive deep into this electronics episodes. So thank you for watching this episode. Kindly subscribe to the channel, like the video, drop your comments. See you in the next episode as we dive deeper into the electronics. Thank you.